Hello everyone, and welcome back to our second class focusing on linear programming. Linear programming, as we discussed, is a method of solving problems that are ultimately looking to optimize choices depending on limitations or constraints governing those choices. Meaning, we're looking to make the perfect choice if in this situation, we're looking to make the perfect choice if we have something limiting our choices. So we looked at one example last time. Let's briefly review that before we move on to some new examples. So to begin, the Beaver Creek Pottery Company is a small crafts company operation run by the Native American Tribal Council. The company employs skilled artisans to produce clay bowls and mugs with authentic Native American designs and colors. The two primary resources used by the company are special pottery clay and skilled labor. Given these limited resources, the company desires to know how many molds and mugs to produce each day in order to maximize profit. The two products have the following resource requirements for production and profit produced per item sold. So we see here the products are bowls and mugs. Labor is one resource. It requires 1 hour for a bowl, 2 hours for a mug. And clay is the second resource. It requires 4 pounds of clay for a bowl, 3 pounds of clay for a mug. And the profit per unit is $40 profit for every bowl and $50 profit for every mug. We see that there are 40 hours of labor and 120 pounds of clay available for each day of production. So this is our basic information given to us. This is a problem that we can solve through linear programming. However, to do that, we have to translate this natural language into a mathematical format that will allow us to solve the problem. So, let's begin. The first thing we have to do is find, there's always 3 steps to follow. Step 1, find the decision variables. And that means, what choices are we making? What are we deciding between? What decision is being made? Step 2, we have to relate those decision variables to our ultimate goal. What are we trying to find? It's our ultimate goal that we're trying to find that determines what the purpose of the question is. And we put our ultimate goal together with our decision variables in our objective function. Once we've found our objective function, step 3 involves looking at the limitations governing our choices. We cannot make choices exactly how we want, because in the real world there are some things that determine what is and is not possible. So for example, let's go in and have a look, work together, and discuss as we go what we are doing. So the first thing we need to do is we have to decide, what are our decision variables? What are we trying to decide? So the company employs skilled artisans to produce clay bowls and mugs. So we see here that we're trying to determine how many bowls we should produce and how many mugs we should produce. this is our ultimate goal. So those become our decision variables. Clay bowls will be equal to x1. Mugs will be equal to x2. Now, we also have another situation. We need to relate these two items to each other. So we have to find out what we are asking. The company desires to know how many bowls and mugs to produce each day to maximize profit. That is our ultimate goal in this situation. So, now that we have our ultimate goal, we have to relate these two products to each other. And we can do that by knowing how much profit each generates. So in this situation, we're trying to maximize Z, or profit. If X1 clay bowls is $40 and X2 mugs is $50. That is our objective function. The third and final step in this situation is we have to find our constraints or limitations. Our constraints or limitations are what govern our choices. It's what tells us what choices are and are not possible. So we see down here, there are 40 hours of labor and 120 pounds of clay available for each day of production. What that tells us is, quite simply, we have only 40 hours of labor. We cannot use any more than 40 hours of labor because that's all we have available. Less is okay. 40 hours exactly is okay. More than 40 hours is not okay. And we see here the same is true of clay. 120 pounds of clay is available. Less is okay. That amount is okay. Nothing more than that is okay. So to do our two constraint equations, we see a bowl is 1 hour of labor, so 1 x1. A mug is 2 hours labor, 2 x2 must be less than or equal to 40. And same for clay, 4 pounds per bowl, 4x1, 3 pounds per mug, 3x2, must be less than or equal to 120. So we've highlighted in this situation all of the key information. Now we have to write it in equation format. We'll do that here. So x1 is the number of clay bowls that manufacture. x2 is the number of mugs that we will manufacture. We saw that before because this is what we don't know. We have to relate them with the objective function. So we're trying to maximize profit if we get $40 per bowl and $50 per mug. But we have two limitations governing our choices. The first one is we have 40 hours of labor available, and 1 hour for every bowl plus 2 hours for every mug must be less than or equal to 40. We have 120 pounds of clay available. 4 pounds of clay for every bowl and 3 pounds of clay for every mug. Total must be less than or equal to 120 pounds of clay. So this is all of the relevant information from this natural language question. We've collected it here, and the final step is writing it in the proper format. Every time we do a question like this, we have to write our equations in exactly the same format. And we see that here. Maximize z equals 40x1 plus 50x2, subject to 1x1 plus 2x2 is less than or equal to 40. 4x1 plus 3x2 is less than or equal to 120. This is quite simply how we have to write all of this information every single time. It has to be written in this format. From here, now we can begin solving the equation in the future, and we can solve it both graphically and mathematically. This was the question we solved last time, and a brief review of that question. What we're going to do today is we're going to move on and solve two additional questions. Several additional questions. So, let's begin. You are the manager of a department store. You sell a combination of clothing and electronics. You are attempting to determine the optimum mix of clothing and electronics to carry in the new year that will allow you to maximize your year-end profit. On average, you make $22 per electronic item that you sell and $6 per clothing item that you sell. You are not free to carry the clothing and electronics that you choose, though. Instead, you have two guidelines, limitations, or constraints that you need to meet in making your decision. First, you have only 50 square feet of display space, and electronics take 10 square feet, while clothing only takes 4 square feet per display. And you have only 40 hours of labor available to set up displays. Electronic displays require 10 hours to set up, while clothing displays require only 8 hours to set up. This here is our natural language question telling us now what information we need to solve this problem in a linear equation format. And that is what we are going to do together now. If you recall from here, the first thing we need to do is find our decision variables. What choices are we making? What is the choice that we have to make? So let's look at our question. You are the manager of a department store. You sell a combination of clothing and electronics. You are attempting to determine the optimum mix of clothing and electronics. So right here we see what we are looking for. We're trying to determine the optimum mix of clothing and electronics. So our decision variable, x1 is equal to clothing, x2 is equal to electronics, because these are the things that we do not yet know. We don't know yet how many of each we're going to carry, so we replace them with the variables x1 and x2. We'll come down here, and for our decision variables, we'll enter x1 is equal to clothing items, x2 is equal to electronic items. Now we see again, as we go back, you are attempting to determine the optimal, once we've found our decision variables, the next step is putting together our objective function. Now, our objective function is how we determine our ultimate goal. In this situation, we want to find what are we ultimately trying to determine. So let's check. You are attempting to determine the optimum mix of clothing and electronics to carry in the new year that will allow you to maximize your year-end profit. So our ultimate goal is maximizing profit. Now, we know we want to determine how much clothing and how much electronics to carry to maximize our year-end profit. But we also have to check. We need our parameters, which is the numerical value, the numbers associated with our two choices. When we have the numerical values associated with our choices, we can then write our objective function. So let's look at this question, and we see on average you make $22 per electronic item and $6 per clothing item. So now we have our numerical values, we have our parameters. From this information, now we can write our objective function. Maximize Z, and Z represents profit, equal to 6x1 clothing items plus 22x2 electronic items. This is what we ultimately want to determine. What will profit be? What will Z be if we have the perfect mix of clothing, X1, and electronics, X2, if clothing is $6 per item and electronics is $22 per item? That is what we're trying to determine. So then we go back and we see that we have limitations governing our choices. If we had no limitations, we would carry an infinite amount of clothing and an infinite amount of electronics. But in real life, that's not possible. We have limits. So we see that we have only 50 square feet of display space available. We see electronics takes 10 square feet and clothing takes 4 square feet. This is our first limitation. Our first limitation is the amount of space we have available to display. We can use 50 feet. We can use less than 50 feet. But we cannot use any more because that's all we have available. So that will control how many or how much electronics and how much clothing we can carry. So we have to write that in an equation format. Let's do that now. So constraints C1 is equal to 4x1, 4 square feet per clothing item, plus 10x2, 10 square feet per electronic item, and it has to be less than or equal to 50, which is the display space available. C2 is equal to, and in this situation we'll go back and we see our second constraint is we have only 40 hours of labor available. Electronics requires 10 hours. Clothing requires 8 hours. So now we have this second constraint governing our choices. We have 40 hours of labor available, 10 hours for electronics, 8 hours for clothing. So one more time, we have to write this in equation format. 8x1 plus 10x2 less than or equal to 40, which is hours available for display setup. So now we've collected all of our relevant information. We have our decision variables, we have our objective function, and we have our constraints. So once we do that, we have one final step. We need to go in and collect all of this information and write it in its proper format. We'll do that here. So we've collected all of our relevant information here. Every time we do a linear programming problem, the format has to be identical. Our problem always has to be written in this format. Now we can add extra information if we'd like. If we want to increase the information, that's possible, but it's optional. It is not necessary. For now, we will add it just until everybody becomes familiar, but it is not necessary in the future. So we're trying to maximize Z, which is profit. We know X1 is clothing. X2 is electronics. We know that here, this is hours, our display space available in square footage. And we see here this is the time available for setup in hours. Again, that information isn't necessary but it may be helpful initially when trying to understand what we are doing. So this is our final problem formulation. From here, we can then solve graphically, which we will do, and mathematically, which we will also do, to determine our optimal mix of clothing and electronics to maximize profit under these limitations. As always, if you have questions about this when you're watching the video, please feel free to contact me through Kakao, and I'll do my best to explain. The last thing we're going to do today, or in this session, is move on to practice example number 2. Again, it's a similar situation, but it is helpful because it does take time and effort and familiarity before you're able to easily translate these problems into the correct formula to solve. So practice example 2. You are the manager of a health clinic where patients stay overnight or longer if they are looking to recover quickly from an illness. You are in charge of ensuring that the patients receive the necessary nutrients in their diet while you are still minimizing your food costs. You have 2 options to choose from when deciding what food to buy. You can buy set A for $10, or you can buy set B for $12. You have to decide on the perfect product mix between sets A and B, knowing that you need 22 grams of vitamin A per person and 38 grams of vitamin C per person. You also know that set A has 2 grams of vitamin A and 6 grams of vitamin C. And set B has 1 gram of vitamin A and 10 grams of vitamin C. So this is our second question. As always, we follow the same 3 steps. Step 1, find our decision variables. What choice is being made? You are the manager of a health clinic. Patients stay overnight, and they're looking to recover quickly. You are in charge of ensuring the patients receive necessary nutrients while also minimizing food costs. You have 2 options to choose from. Key information. You can buy set A, set B. These are our 2 choices, which makes them our decision variables. So let's go over here and write in our decision variables. Which is set A, and that is, we'll do it the other way just for simplicity. X1 equal to set A. X2 equal to set B. That's what we've seen so far. Now, once we have set A and set B, we have to relate them to our ultimate goal. So let's go back. Let's determine our ultimate goal. You are in charge, so this is what we have to decide. Ensuring that the patients receive the necessary nutrients in their diet while still minimizing food costs. So this question is a little different. We're not maximizing this time, we're minimizing. And in this situation, we have two options to choose from when we decide what food we can buy. So now we know we're trying to minimize, and we know we have to buy set A or set B, but we have to include the parameters, which is our numerical values associated with this problem. And we see our numerical values. Set A is $10. Set B is $12. So we see here that we have all the relevant information. We're trying to minimize food costs if set A is $10 and set B is $12. So from here, we can go in and we can write our objective function. Minimize Z, which is cost, if set A is $10 and set B is $12. If this is all correct, then we have a minimization situation and our objective function is complete. Our third and final step is determining constraints. We know already that if we're trying to minimize costs and we have no limits, very simply, we would buy nothing. If we're trying to minimize costs, spending no money is the easy answer. However, that's not an option for us. Instead, we see that our constraint situation, we have to ensure that patients receive the necessary nutrients. That is a limitation. We can't buy zero because if we buy zero, people can't eat. So instead, we have to look at what nutrients they require. So you have to decide on the perfect product mix between sets A and B, knowing that you need 22 grams of vitamin A per person and 38 grams of vitamin C per person. Suddenly, we know what is required. This cannot be ignored. These are our limitations. Set A has 2 grams of vitamin B, vitamin A. Set B has 1 gram of vitamin A. So now we know that we see here we require 22 grams. A has 2 grams, B has 1 gram. We can write our first constraint. So we see here that we have 2 grams per set A of vitamin A and 1 gram in set B of vitamin A, and we require more than or equal to 22 grams. Last time it was less than because that's all we had available. This time it's greater than or equal to because this is the minimum amount necessary. So let's go back and do our second constraint, C2. From C2 we see 38 grams of vitamin C per person is also required. Set A has 6 grams of vitamin C. Set B has 10 grams of vitamin C. So we see here, now we have our second constraint. We require more than or a minimum of 30 grams of vitamin C. We know there are 6 grams of vitamin C in set A and 10 grams of vitamin C in set B. So we can go in and we can write our second constraint. Okay, so once again, we've taken this natural language question. We've highlighted all the key points, and the key points you will get better at recognizing over time. A lot of this is practice and pattern recognition. But once you have the key points, you highlight them, and you follow these 3 steps. What are our decision variables? What is our objective function? What constraints should we follow when making our decisions? Once we have this critical information, very simply we go down and we collect all of that information in one place. And that's what we've done here. This right here is all of the key information from this question written in the correct formula or in order to solve these problems. Now, this is enough. This is exactly where you can finish. For simplicity and for comprehension right now, I'm going to add some extra information just to make it a little more clear. In this situation, Z represents cost. X1 represents set A. X2 represents set B. One more time, X1 is set A. X2 is set B. And 22 is our required grams of vitamin A. One more time. X1 is set A. X2 is set B. And we require 38 is the required grams of vitamin C. So none of this information was necessary, but for comprehension, it should be helpful. This is another example of a linear programming translation of natural language to mathematical equations necessary for solving. Hopefully everybody understands. If there are any questions, as always, feel free to reach out to me in Cacao. We will continue this in our next session. Thank you everyone for listening, and I'll see you shortly.